Okay, so let's just remember at the beginning of these exams there are a lot of these kind of conceptual types of questions. So you don't want to screw up on the easy ones. So that's kind of where this beginning stuff is coming from. Okay. Oxidation numbers of atoms in a compound, right? How do you figure these out? Do you remember? Oxygen, that's the starting point. Excellent. Oxygen's -2. See if you can figure out what they all are, and then I'll write. That's an excellent starting point. Right? Yeah, right off the bat, that's true. You could recognize copper as +2 right away. The only way to know that is if you remember sulfate has a -2 charge. So you know copper has to be +2. But usually, right? So I'd have a -8. Yeah. Sulfur would have to be +6. The only way to know, I think, well, there's also a possibility for copper being +1, right? So you got a 50-50 shot there. But if you memorize sulfate's -2, you're set. Add up all the oxidation states, they have to add up to the overall charge. Pretty much, and that's usually how it works.
Like, could you break it down into like SO4 by itself?
You could do this. Yes, you could just do sulfate, but remember it has a -2 charge. So you'd have a -2 for the oxygen, -8, and +6. Yep. You'd have to add it to be the charge.
Copper one, you knew just.
Yeah, because it has to be, sulfate has to be a -2 charge, so copper must be a +2. P2O5, oxygen's always -2. So phosphorus has to be plus -10, has to be a +10, +5, good. Right? Okay. Let's try, yeah, because 2 times +5 is +10. So this side you know is -10. This side has to be +10. So if that side's +10, that means each phosphorus has to be +5. You see? Make sense? Okay, how about put a box around the reducing agent. The reducing agent, put a box around it in this reaction. Put a box around the reducing agent. If you're calculating something, you kind of miss the point of the question. Oh, no, there isn't. Oh, I thought that was manganese +3. It's not. You are going to have to calculate something, aren't you? Whoops. I thought that was manganese +3, but it's bismuth. So you're going to have to calculate one of them. So what did you get? Did you do bismuth? Did you find it out to be +5? Okay. It's +3 here. It's +5 here. Why do I want to circle anything? This compound got reduced. So it is the oxidizing agent. So we better draw a box around Mn2+. Okay, remember that kind of thing? Charge, current, voltage, power. See, bismuth went from +5 to +3. So this compound got reduced. So this compound is the oxidizing agent. So I want to know what the reducing agent is, so that's why I drew a box around the other guy. He has to be. So you can figure out what he is over here, and he had to get oxidized. Okay. Looks like it's locked up. How about, so I give you these equations, but what are the units for all this stuff? Like what is, oh, V is volts. How about I? Current, but what are, it's an amp, but know what an amp is. There, that will really help you out. Amp, number of coulombs over number of seconds. You're right, an amp is a coulomb per second, but it's really an equation. Amp is the number of coulombs divided by the number of seconds that elapse for that charge to pass by. So, power. Watts, which was what per what? Yeah. Joules per second. Good. A watt, which is work per unit time, how much work can get done per unit time, but work is energy, joules per second. Okay. How about 1 mole of electrons? How much charge is that? Yeah, 1 mole of electrons. What's the unit of charge? Coulombs. So you better give me a number for coulombs. 96,485. Well, 9.6485 times 10 to the fourth, the same thing. Yep. 96,485 coulombs. Galvanic cells. Typical relations include. Okay. What if? How do you get E cell again? Yeah, you want it to be positive. That means it'll be natural, right? It'll be spontaneous. They call that a what cell? It starts with a G. Galvanic. What if it was negative? Ah, that's true. That's true. What if it? Can it be negative? Can E cell be negative? It can be. You just got to force it to happen, right? You have to force that reaction to happen electrochemically, because it wouldn't be spontaneous. Where do we get this E cell number from?
By using the E0 cell.
Oh, you could use Nernst. That's one way. Okay, we should write these guys down. Nernst is one. That's one way to get E cell. Right? E cell is E0 cell minus 0.0592 all over n log of Q. Okay. Now that, so you can get the voltmeter, Nernst equation. Okay, now if you use a table, that isn't E cell anymore, that's E0 cell. That's the standard. If you use the table. So then if this is E0, it has to be delta G0. Okay. So I'm only giving you one of those equations, just telling you what's going on here. If it is this equation, what's the little n? Number of moles of electrons. That. Yeah, because it's really per mole. All this stuff is per mole, so it's the number of moles of electrons that canceled out when you got that standard E0 cell. Okay. How about name 3 reducing agents? And might as well just do this. Jump right to B. Name 3 reducing agents and list them in order of increasing strength. All right. You're supposed to be looking at this table. Where should you be looking? Should be looking at the reactants or the products? All right. Reducing agents, that means they had to have got oxidized. So you have to be looking at something that got oxidized. It's the products. Because all these tables are always standard reduction potentials. Everything's getting reduced. So if you want to find a reducing agent, something that can reduce something else by getting oxidized, find a reducing agent, it has to get oxidized. So you just pick any three things. Yes, for that E0. E0 would be flipped. It would be nice if they gave us two tables, but it'd be kind of redundant. Okay. So if I pick these three, or whichever three you picked, how do you order them in order of increasing strength? Yeah, so I guess first we should flip them all in our head, right? So you have this chromium is really, it's negative 0.2. This tin reaction would be negative 0.13. Because I'd have to flip the whole reaction, right? Make this guy a reactant, right? Okay. Oh, I picked the wrong one. Look at that. He's combined with silver. Right? That's not a good one to pick. All right. Let's pick one who's copper solid. That makes some more sense. That's negative 0.34, positive 0.14. So who would, the weakest out of the bunch would be? Copper solid would be the weakest, the least reactive when it comes to being a reducing agent, right? And then go on down. Okay? So the same idea for C and D. Same kind of thinking. In humid environments, does the following happen naturally? And at first I thought I was being mean and making a trick question. I thought this electron is on the product side, this one's on the product side. Well, then it ain't going to happen, right? Because one has to be producing electrons, the other one has to be reacting with them. But at least, yeah, electrons are opposite sides, so it's not a trick question. And you say yes because E0 cell's positive. Yeah, you can't stop it from happening. And then you can find the overall reaction. And how would you do that? Kevin, how would you do that? Exactly. You're interfering. If you guys want to talk, there's the hallway. Okay? I have no problem with that. How do we get the overall reaction? Pretty much just do what? Yeah, cancel out the electrons, add them up. Okay? Where are we now? From a table standard reduction potentials. Okay. You don't want more reactive than iron solid. You don't want this to react. So you just pretty much find a metal that has what? Higher, more positive E0. More positive 0.44. Like zinc. I think we did that in class.
When you're writing overall reaction, do you have to balance out H2Os and OH minuses? No, right?
No, they are balanced. It will work out. It will work out. Multiply this one through by 2, add them up, electrons cancel. It will work out. Okay. Yeah, you just don't include them in a Q expression, solids and pure liquids. Okay, how about EX4? In a beaker, this stuff was all dumped together. The pH is adjusted to 4.5. What reaction is most likely to occur within the beaker? There's got to be some game plan for this. Would we what? Yeah, there you go. Find the half reactions. And then manipulate them to see how you get the greatest E0 cell. Exactly what Javier said. So half reactions that involve these, right? You've got iron, you've got manganese, and you've got cesium. Okay, so you got some choices to look at. It might be the most straightforward to actually write all those half reactions down. I think I got a table. See if you can find them. somewhere. If I would have been quicker if I would have just wrote them down somewhere. But that's part of, see, that's another thing I think it's good for you to do, because this is what you're getting on the exam. One of the toughest, it really complicates things when you got to dig for your own half reactions. And this is what you're getting on the exam, right? So you got to dig up your own half reactions and find them and write down their E zeros. Okay, so if you got the book, I suggest trying that with this, right? See if you can find the half reactions and dig them out. Or you can, I need these back though, right? You can take these and find them, but I need them back because I need them for the exam. So, and don't write on them. So, see if you can find them. 1, 2, 3. And I gave you 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
So it should be 3 different half reactions, right?
Yeah. Find all 3 of those half reactions. Man, I may not have enough. And good thing I did this now. Otherwise, now I wouldn't have one for the exam. Got 4. You can borrow. Oh, I've got some right here. What the heck? Hmm? Use what?
We're gonna have to use it.
Oh, okay. So see if you can find them. Write them down. Manganese plus 2. Manganese plus 2. Yep. Yeah, you're gonna have to write down all 3.
Is it 1.72?
Oh, but it tells you the concentration of H plus. pH is 4.5. Ah. Picked a bad
Does it
one.
matter that the pH?
Because the pH would tell you the concentration. We don't know what the acid is, so you're just gonna have to pick 1.72 because you don't know what the acid is, right? It would have to be. It'd have to be one formal, all that stuff. Otherwise, it's 1.72. Yeah, it's gonna have to be 1.72. Yep. We have to write down the whole thing. You have to write down the whole half reaction. Where is it? What is that? CE cerium. You're going to have to pick, on the cerium, you're going to have to pick 1.72 because they didn't tell you the formal, you just know the pH is 4.5. You don't know what the, it's not going to be one formal anything. So it's going to have to be the 1.72. Okay. Now the manganese. Manganese had another one. Okay, so I wrote down all of these three. See if you agree with me so far. I just copied down the reduction potentials. Now I have 4. I don't know if you recognize to write down this one or not. This half reaction can occur, but only in what direction? Only in this direction. Why? Because if I want to go this way, I better have what present? Manganese dioxide. There's nothing stopping this reaction from occurring in this forward direction, though. So that's why I wrote it down, because there's nothing stopping it. But there is, it's not going to go this way because there isn't any manganese dioxide. Makes sense? So that's why I wrote it down. Well, no, it's up there. I wrote it up there, too. So I just added this one at the end because I thought, hey, what's stopping this one from happening? Okay. Oh, did I script the permanganate one on top? Permanganate, 8 hydrogen ions plus 5 electrons goes to manganese plus 2. Okay. Okay, so now what's the name of the game? You want to get the most positive E0. That's what nature's going to do. Well, I don't know if I'm going to need it or not. Because I know that this forward reaction can occur, the other one can't. So it's a possible reaction. Okay, now I haven't picked anything yet. I just wrote down all my possibilities. So in nature, what's going to happen? You get the most positive E0 cell. Okay, so you need a reduction and you need an oxidation. So you can, one thing you can do is you can flip all these. Let's do that one first. Right? If you flip all these reactions, all the signs change. Which one would be the most positive? The positive 0.44. So it seems to me your oxidation reaction is going to have to be that top one flipped. Because this is your only choice. Does that make sense? So we'll be flipping this one. That'll be my oxidation half reaction. So now I need to pick a reduction half reaction. Which one's going to happen first? Cerium. Because it's the most positive. That's the game plan you pick. And see, we could have ended up using this one. It was close. There's nothing stopping it. Right? And who cares? Like, and I know the ramifications of it. This wouldn't show up in the Q expression anyway. But we don't have any of this to form, so it definitely couldn't go that way. But it could go in the forward direction. So this will be my reduction half reaction. Okay. So what reaction is most likely to occur? So go ahead and add them up. Get the overall reaction. Right? These two. and go ahead and see if you can get delta G0 and the rest of it.
So when we're setting this up, do we only include those two equations there for our G setup?
Where would G set up? What are you talking about?
Okay. So when we're calculating the total E cell, are we going to just use those two equations?
That's the reaction that's going to happen first.
Right.
So find the equilibrium constant for the proposed reaction. You haven't written one yet. So you have to add these two up. There isn't one up here yet, right? Or write your overall reaction. Find delta G0 for that overall reaction that you just wrote.
No, I was just saying, like, so what's the name of the C guy? What's his name? Anyways, I'm just saying, like, that'll occur at a faster rate. Won't necessarily occur first, you know?
It's an odd thing. It does. And how does it? We have an instrument over there. It's called a potentiostat. And what it does is if you're at this potential, this reaction actually happens, but the others don't. So they're just sitting in there, and it's an oddball thing. So it's kind of that's why iron won't rust, right? That last tidbit of zinc has to disappear.
The cerium has to react in this case.
And now I'm sure there's going to be matrix effects where it's going to think cerium isn't there anymore, just like with a rusting nail. There might be a tidbit of.
Right, it depends on
So I think you've got spatial considerations and mixing and all that stuff going on. But for our purposes, we're just saying no. Instantly, I guess maybe think of it this way. The first instant in time, this is what's happening. You're right, because life is going to get much more complicated later. And F is that Faraday's constant.
Okay.
Because we need to convert moles of electrons into coulombs.
Okay, so just Faraday's constant.
Goes to iron, not to iron.
So Zach brought up a good point. I don't know if you thought what he was talking about is you can't. This is the predominant reaction. It's the most spontaneous. So that's really what we're driving at, right?
You're not going to fix it all because you're only going to use an oxidation. So in the overall, we do write out the solvents.
Yeah, it's the overall reaction. Okay. Then find your delta G0. Oh, find the equilibrium constant. What is this delta G0 even doing in there? Right? Find the equilibrium constant for the proposed reaction. It's asking for equilibrium constant. So what is that even doing in there? Find the equilibrium constant. Mm-hmm. Add what? Yeah, you have to add them up. Gosh, no wonder that's so messed up on that grading. That's why I can't do anything in my head. Yep.
Why do we not
it's kind of it's a potential. It's if you an intensive property versus an extensive property.
Okay, so it's not affected by changes in
Like density, it doesn't matter how much you have.
it's always that
It's always like that. So it since it's being an intensive property, that's what allows something like the potential stat over there to work. If you get a little peak right at 1.72 volts, you know it could be this reaction progressing and nothing else. Yes, Jamie. Why I picked that reaction? Okay. Yeah. So to pick the reaction, right? We could do it the other way around first. Let's pick the reduction reaction first, since they're all reductions anyway. It's kind of easier. The reduction reaction, because you have to have a reduction and an oxidation, right? The reduction one, they're all written as reduction reactions, correct? So you pick the most positive. So that would be the cesium. Boom, it has to be the cesium. He's the most positive. And then if you flip them, which one's the most positive? The iron. So that's why we're doing those two. Okay? Well, you need a reduction reaction, half reaction. So you pick it the most positive. And then you need an oxidation half reaction, but remember all these are flipped. So really you're picking the most negative one. Does that make sense? Because we're not rewriting the whole table again for oxidation.
So we flip the first one because we're oxidizing it, right?
Yes.
But we don't flip the second one?
Well, if you flipped it, the electrons wouldn't cancel.
Okay.
Because you need a reduction and an oxidation reaction, half reaction. Have to have one of each.
All right, so that middle one is just totally just pretty much omitted since we don't need it, right?
We don't need the permanganate half reactions at all. Yeah. But we needed to write them down just to compare.
Check it out to compare.
So you remember how to get equilibrium constant? Do you remember how to get equilibrium constant? E cell has to be what number? At equilibrium, E cell, you measure on the voltmeter, it's a dead battery. It's at equilibrium. 0. So this is 0. We're at equilibrium, so Q now becomes K. So your equation to get the equilibrium constant, bring this over to the other side, right? Your negative signs might cancel, or they will cancel. So E0 cell would equal 0.0592 over N log of K. Right? That's your expression for the equilibrium constant expression. Well, this is, bring this over to the other side, it'll be negative, and your negative signs will cancel out. So you can get your K. Once you get your K, see if you remember how to write your line diagrams, right, for a cell description. Where you have the double line for the salt bridge. It's going to be huge. And it should be huge. It should be huge, right? Because look at that. Potential is tremendous. 2 volts? Okay. Add a negative E0 cell to both sides. You get a negative E0 cell. You have a negative sign here. Those negatives end up canceling. You should get a huge, huge K. 2 volts is a tremendous potential. Okay. So see if you can write your cell diagram. See if you agree with what I'm going to write. Yeah, see if you'll match what I'm going to write on here. Write that cell diagram. Yeah, for part C. Yes. So if I add, this is 0, I'll end up with a negative E0 cell equals a negative 0.0592 over n log of Q, right? So negatives end up canceling out on you.
So we're just doing anode on the left, right?
Yes, anode has to be on the left. And anode is oxidation. Okay, so find your oxidation half reaction and write it out. What is it? 2, 3.
Does it matter like how we format the molarities? When we put them in? It goes like that, parentheses after.
Oh, that's what they did. They like parentheses. Yes. If you know it, right? What was the rest? Reduction half reaction was cesium.
They don't say there's a cell bridge, or just assume there's a cell bridge.
Yeah, there has to be a salt bridge. What is cesium plus 4? 0.29 molar. Okay. So in D, in order for the question D to make sense, we needed to have picked a half reaction that involved pH, but we don't, right? I thought we were gonna, but we didn't. Because if we had pH in here, like let's say the cesium half reaction had a specific, it had a hydrogen ion in it, you had to describe the pH. Okay? It did. That's what I thought we were going to pick, but we didn't. Right? So I thought we were going to pick a permanganate half reaction. So a permanganate half reaction would have been over here on the oxidation side. That's what I thought was going to happen. Right? And so then, you know what the pH is? You calculate the Nernst equation and find the potential E. So this question, this part has to be omitted because it doesn't make sense. We're already done. Oh no, we know the concentrations. We can do that, right? They're not. What is it called? Standard. Yeah, I was thinking E cell. So yeah, we can get E cell. That's right. It's not going to be E0 cell. That pH is what we didn't matter. That's what's confusing me. The pH didn't even fit. Okay. The pH didn't even fit. Here it is. And we know the overall reaction, so we can calculate products over reactants, their concentrations. All right, here's what you'd write Q for. Leaving out solids. Yeah, and make sure you square the cesium-3 and square the cesium-4, because there's two of them. Right? Concentrations raised to their stoichiometric powers. I think it was 2. Products of reactants, cesium plus 3 squared. And that's my other product. Iron 2.23. Reactants, just iron, cesium plus 4.29, and the other reactant was what? Well, that was it, just cesium plus 4. We don't need pH, it's not in there. I guess you could write pH because they gave us the pH. It doesn't hurt. What did they say it was? 4.5. So there's a bunch in here to practice on.
Balancing the redox reactions, is that the...
We didn't spend any time really on this. So I would say you could omit this stuff. Because we didn't have homework on it, right? So this would be busy work. My son gets a lot of that. Okay. So combine, lab tomorrow at night and early, 8 a.m. Yep.